You must have faced this situation, where a zipper is clearly zipped up, but the moment you let go, it splits open right down the middle. Your first reaction must be that the zipper teeth are broken, but strangely, if you zip it again, it sometimes goes back to normal. If the teeth are truly broken, why can it lock together again? And if they aren't broken, why does it split open on its own? The thing that's actually broken is something you almost never suspect. Many believe zippers stay closed because the teeth bite tightly enough. But you've fallen into a misconception, as structure locks it, never sheer force. Before zippers were invented, buttons, knots, and clasps ruled the clothing world. They all secured clothes, but shared one flaw: having too few connection points. Buttons are fastened one by one, concentrating the stress. Tighter knots are harder to untie. And clasps are convenient, but barely seal. Until the late 19th century, people began trying a brand new approach. What if instead of a few points, hundreds of connection points worked together? After many failures and tweaks, Gideon Sundback designed the modern zipper prototype. What changed the world wasn't a row of metal teeth, but a continuous interlocking structure, so connection no longer relies on one point, letting hundreds share the load. So how on earth does it actually do that? Many think the two rows of teeth just bite into each other, but no. Take two combs and interlock their teeth. They look joined together, but with a gentle pull, they separate instantly, because they just touch without locking. Magnify a zipper, you'll see each tooth is like a block with ridges and grooves. When the slider passes, it doesn't just squeeze the two rows together, but acts like a miniature assembly machine, rearranging both sides of teeth and locking them precisely into each other's grooves, creating interlocking rather than contact. Better yet, each tooth connects opposite while being restricted by those ahead and behind, so tooth by tooth, row by row, they form a continuous whole. This means when you pull hard on clothes, force won't focus on one tooth, but spreads rapidly across the entire zipper. Tension once borne by a single point is now shared by hundreds of joints, so what truly bears the force is not one tooth, but the whole structure. But why doesn't the zipper slide down when running, jumping, or bending over? The truly clever part is actually hidden inside the slider. Many modern zippers use auto-lock sliders. When you pull the tab down, a tiny locking mechanism catches automatically, making the slider unable to move. Only when you actively lift the tab will it release the lock. That is, when clothes are pulled, force acts between teeth instead of pushing the slider. Engineers call this auto-lock. It shifts force direction rather than increasing strength. Truly great design never fights force with force, but leaves faulty force nowhere to act. If you think this is clever enough, here is a counterintuitive question. Why do many zippers split from the middle even without missing teeth? Many blame per tooth quality, but most of the time the slider is worn out. After long use, the inside of the slider stretches slightly wider. A change under 1 millimeter keeps the rows from fully closing. They look connected but are half-locked, which is unnoticeable at first, but once clothes are pulled, unlocked teeth unfasten one by one, and the whole zipper splits apart all the way through the middle. So, experienced zipper repairmen won't replace the entire zipper immediately, but use tools to gently squeeze both sides of the slider first. Because the teeth might not fail, but the part managing their connection does. This concept can be seen everywhere in modern industry. Why can a car jack easily lift a vehicle weighing several tons? Why don't heavy loads drop instantly when cranes lose power? Why do woodworking clamps tighten more as you turn them? They don't use greater force, but let structures redistribute and reuse it, even letting the force turn back to lock itself. The same mechanical philosophy just takes on a different appearance. More interestingly, nature used similar methods a long time ago. Why do bird feathers smooth out after a few strokes when ruffled by wind? Because each barb is covered in tiny hooks that relatch to each other. This interlocking structure allows separation and quick reconnection. Engineers kept studying these natural structures, gaining much design inspiration. A tiny zipper connects mechanical design, precision manufacturing, biology, and modern engineering. What changed the world wasn't metal teeth, but a mindset about structure. Instinct suggests things are sturdy because they are harder, thicker, and stronger. But engineering proves reliable systems rely on structure, not brute force. Structure distributes force, limits movement, and tolerates errors. It can even let force turn around to protect itself. So, next time you pull up a common zipper, change your perspective. You close a precise system optimized by countless engineers over a century. Many world-changing inventions succeed not because they have the strongest force, but because they found a much smarter structure. What other low-profile design in things you touch every day actually hides the same brilliant engineering wisdom?